Students, welcome to the final part of today's class. We have been doing Q value of a reaction, and we are finally right to the expression, and we will be looking at certain very small points connected with it, and after that we'll move on to do the next topic, that is proton induced reactions. Now looking at this one, we were here actually. So this was our equation 3 which we had taken at the very beginning, and then what we did is we had found this considering the conservation of energy and momentum, and after that instead of EY, when I substitute EY out here, because we get this one which is the final expression. It may look very difficult, but no, it's not like that, because we have EY here. And you see we have EY here and EY here also and here also. So we have My by capital My, and we have a component 1, so we get this term, and similarly for Ex also we get like that. E small x, we have Mx My, and we have like this negative. So this comes with a negative term, and this is the final expression. Now there will be a number of small points, such as when you are observing the outcoming particles at 90 degrees. Suppose the outcoming particle is at 90 degrees. Your outcoming particle means this y, it came out like this, and this was theta. So when the outcoming particles at 90 degrees, that means theta is equal to 90 degrees, which makes cos theta is equal to 0. So cos theta is equal to 0 means we won't be having this term, and it will just be this much. So in case the outcoming particle comes out at 90 degree, the expression gets reduced to this one, and there again will be cases like when we have elastic collision. What will happen in elastic collision? In elastic collision, in which suppose Mx is equal to My and Mx is equal to Mx. Why it will be like this? Because in elastic collision there is no change in the particles. We already know that. You see that X targets capital X, and we have again X, and we'll again have X and X. So in that case, you see the particles will be same, and we will find that Q is equal to 0. So again, in elastic collision it will be slightly different, but if the particles are same, particles remain same without changing, then also we have some. So this will remain as your homework. You will do the different cases, and I have also shared it, the study material, to you. So with this we come to an end to the Q value part, and we'll go to the proton and alpha induced reaction. First let's do the alpha induced reaction. So even though I have said that I'll do the proton induced reaction, we can do it later. First let's do the alpha induced reaction. So please look at certain small points which in connection with Q value of nuclear reactions, which has been shared for you. Now going to the alpha induced reaction, because we have already seen an alpha induced reaction earlier, so I want to start from alpha induced reactions. Now students, we had seen a very simple equation where this plus this gives us y plus y. Now this can also be written in short like this. This is a way of writing up. So this is the incident particle, and this is the product particle. So some people write it this way, and some others choose to write in a different way. They write it like this. Suppose I have, in a more detailed manner, they write it like this: Z, so X plus this gives you Y. Here they write A dash and Z dash. Obviously they will be different because they are different nucleus, different elements plus Y. So in that case, this reaction is also written like this: AX X comma Y A dash Y. Some write it like this, but I prefer to write it in this manner and in this manner. So that is about it. And one more thing is that do you remember the first equation that I had shared with you in the part A of today's class, that this was the first reaction and it is the starting point of a nuclear reaction that was induced, and this gave us, this was done by Rutherford. So this is a historic equation actually, and this is a, look at this, this is nothing but an alpha particle, and this is a proton. A proton is shown like this, the proton nucleus. So here we are not talking about the whole atom, these are the actually nucleus. These resemble, these actually they designate the nucleus like this. So this is a, if I write an equation like this as X and Y, this kind of reaction will obviously be written as alpha P, isn't it? So alpha and P. So this is an alpha induced reaction, and here proton is emitted as a result of this as a product particle. So let me clean my board. I'll give you an idea about different types of alpha induced reactions. So alpha induced reactions, we have number of types. Type A is alpha P reactions. So alpha P reactions are also written like this: alpha P reactions, and this is like this. So what happens is that first the alpha particle hits the target nucleus, and after that what happens? A compound nucleus is formed. That means alpha is absorbed by this one according to the compound nucleus theory of nuclear reactions, which we will see after some time. So this absorb this particle. After that, since due to the absorption of this energy, what happens here is that since this is in a high velocity, it's with great momentum, so this nucleus, although it absorbs it, because this enters inside this nucleus, this are set to vibrations because of this high energy, and it's because of its high energy it cannot be sustained and it breaks up like this. This is in an excited state, so it is emitted. So as a result we have another nucleus along with emission of a proton. This is what happens, and these are like, I'll give you two or three examples. Suppose this one. This is boron, and when I hit it with an alpha particle, the reaction can be written in this manner. This obviously becomes 10 plus 4 is 14, and 5 plus 2 is 7. 7 atomic number, we have this nitrogen, but it will be in excited state. Why? Because of the reason that I told just now, because this alpha particle, which is highly energetic, it will be absorbed and it will be in a highly energetic state, and therefore it will have to come down to the ground state. Okay, let me find some space out here. So this becomes like this. Proton plus some amount of energy plus energy. In this case, this energy is equal to 4.04 MeV, and you really don't have to calculate this. You don't have to memorize this. This can also be found by using the binding energy formula. Now here, how do I know that this is like this? Because you see, since it is an alpha p reaction, it will be hit by an alpha, and it will become like this. This gets added to this and we get this. This gets added to this, we get this. And after that, what happens? I know that a proton has to come out here. So I write the proton here like this, 1H1. And from here I subtract 1 from here, 1 from here, and I get the resulting Y out here. This is X, this is small x, and this is small y. This is how you write. So let's try another one. Another one is, suppose I have potassium with 39, it is okay, 19. For this, immediately when I write this, I can write the whole equation. Let us see what it will be. Because it's alpha induced reaction, I have to hit it with alpha particles, and we know what will come here. It will come here 39 plus 4, so it will be 43, and in the denominator, or not denominator, in the bottom we will have 21. So 21, we have this element. So you have to remember some, I'm sure you remember this atomic, the corresponding element corresponding to a particular particular atomic number. So after that, what do? We just write something 1H1. So since this has to be 1H1, I have to subtract this from here, so this becomes 42, and then here we have 20. And what does this correspond to? Z is equal to 20. It's nothing but it's calcium. So that's how you write a alpha p reaction. So that is alpha p reactions. We are under students. Let me remind you that we are doing alpha induced reactions, and alpha induced reactions are of many types. We have done just one, that is alpha p reactions. So similarly, we have the other type of alpha induced reaction, that is the alpha n reactions. This is the alpha n reactions. So in this case, we take an example. Suppose lithium plus you have a neutron. And how do we write a neutron? We write a, okay, I'm so sorry, it's not hit by a neutron, because this alpha reaction has to be hit by an alpha particle. It's the product particle that is going to be a neutron. So I'm sorry for what I said. He, this is invariably the alpha particle, and then here we add up. When we add up, what do we get? We get 11 here, and we get 5 here, and corresponding to 5, what do we have? Obviously we have boron, and it will remain in an excited state. So it is like this. And here, as a byproduct, what I know that it's going to be neutron, because it's a alpha n reactions, and we will have Q value. So if I do this n1, so this has to be 11 minus 1, which is 10, and here we have 5 itself. So it's the same element, because this determines what element it is. So like this, it's boron. That means this is boron, it is red state, and this is in its excited state. So